Right, so in looking at the long-run behavior of rational functions, with it being in the form polynomial over polynomial, you'll be able to tell this long-run behavior if you compare leading terms of each polynomial. The one in the numerator and the one in the denominator. And one of three things will happen. So, if, for example, you have 6x to the fourth plus x cubed minus 1 over 5x plus 2x squared. If you can pick out the leading term in the numerator and the leading term in the denominator, and if you have where the degree in the numerator is larger than the degree in the denominator, then what that's going to result in is that long-run behavior of whichever direction the function goes will be to infinity. There will be no sort of asymptote. There will be no sort of restriction as to what the ends will be. So the long-run behavior will end up going to infinity here. Okay, and that's if the top degree is bigger than the bottom degree. The top will grow a whole lot faster than the bottom. The numbers will get huge. And then you can take and look at like 6x to the fourth over 2x squared, and that's like 3x squared. So the long-run behavior will have that same property of whatever that looks like. Okay. Right, so it takes on the behavior as either x goes to infinity or as x goes to negative infinity. The long-run behavior goes up positive to positive infinity. And that'll happen every single time the degree of the numerator is larger than the degree of the denominator. An alternate to that is going to be when they're equal. So if you have the highest degree in the numerator is equal to the highest degree of the polynomial in the denominator, what's going to happen there is a horizontal asymptote will happen. And a horizontal asymptote is a horizontal line. I mean, it's imaginary, you know, y equals whatever that number is, it's dotted, but it's a horizontal line that the function can cross. It doesn't have to. It can cross at some point, but in the long run, the function will just approach those values, sort of like in a limit sense. So, for example, if you had the function x plus 3 over x plus 2, you know, that's a rational function. You could find the domain, you could find the x-intercepts, you could find any vertical asymptotes. Remember, vertical asymptotes come from things that make the denominator undefined. But if we're looking for the long-run behavior here, you can focus on those leading terms, and in this case they're both single x's. And if you look at this coefficients, you do a horizontal asymptote of those coefficients. So, you know, x over x would pull 1 over 1. So at y equals 1, there's a horizontal asymptote for this graph, you know, depending on what the actual picture of it looks like. This one, for example, I mean, you can graph it if you like. Do parentheses of x plus 3 over x plus 2. Get a graph going. You know, it has, you know, space over here, and then it has this other piece over here. But it has this vertical asymptote of y equals 1. So as either x gets infinitely large or as x gets infinitely large in the negative sense, the function value for both of these goes to 1. And that's just coming from the fact that the leading terms were the same power, and we pulled their coefficients off, and that gave us the equation for a horizontal asymptote. Let me do another one of these where they're equal. Say, for example, you had y equals, let's see, where's one where here we go, 3x minus 4 over x minus 1. And you were looking at the long run behavior of this function. And again, long run behavior is just what the function does as x goes to infinity. What does the y function do? And as x goes to negative infinity, what happens to the function values? So if you pull and compare the fact that the top has a leading term of 3x, the bottom has a leading term of x. Again, leading term is the one where the highest exponent lives. 3x over x, pull the coefficients, it's 3 over 1. You get the value of 3. There is a horizontal asymptote at y equals 3 where, here's 3. There's a vertical asymptote at x equals 1 because x can't equal 1. So we can draw 1 at 1 if you like. And you can graph this if you want to see exactly what it does. You don't have to because we have the characteristics from the graph. But a lot of times these rational functions will have this split. So there's this upper piece and then there's this lower piece. And you'll see as the x values, here's x, as the x values get larger and larger and larger, the graph will try to approach this horizontal line of y equals 3. And then alternatively, as the x values get smaller and smaller and smaller, they try to approach that horizontal line at 3. So for this one, the long run behavior, as x goes to infinity, the function value approaches 3, and as x goes to negative infinity, it still tries to approach 3. And all you're doing is pulling the coefficients from those leading terms in each of the polynomials to come up with what that would be for the asymptote. It'll help you with limit behavior and things of that nature. All right. The other option, the third option that you'll have for long run behavior is if the degree in the numerator is less than the degree in the denominator. In other words, you've got, x over x squared, or x squared over x cubed, or x over x to the fifth, whatever the nature of the setup. If the bottom has a higher power, the denominator will get bigger faster, which means your fraction will get smaller faster. And anytime you have this relationship happen, it will always result in a horizontal asymptote of y equals 0. And so as x tries to get large, positive, or negative infinity, the function value will go to 0. And it'll have, again, the horizontal asymptote at 0. And depending on how the equation is set up, the graph will try to approach 0 horizontally from both as x goes to infinity or as x goes to negative infinity. It'll approach that asymptote of y equals 0. But that's only if the degree of the numerator is smaller and the degree on the denominator is larger for wherever your leading coefficient is. And that happens every single time on those. Just the bottom, the denominator grows faster. So you're able to pull horizontal asymptotes. Remember, horizontal asymptotes you can find from those leading terms and comparing their powers. Compare powers, maybe coefficients when they're the same. Vertical asymptotes are those undefined domain places. So it's undefined whenever the denominator equals 0. That's also going to be, let's see, Y-intercepts you could find from a graph. Y-intercepts, if you remember, are where the x value is 0, so it would be the point 0, comma, wherever it crosses the y-axis, And in a rational function, you're also going to be able to take x-intercepts, and that's going to be where the top, that p of x polynomial, has zeros. So we can look at one of those if you like. It's like, for example, y equals x minus 1 over x plus 3, x minus 2. All right. Long run behavior. If you want to expand out the bottom, you can, just so you can get an idea. But the bottom will end up being x squared plus x minus 6. You have the degree of the top is smaller than the degree of the bottom. So you're going to have horizontal asymptote at y equals 0. Because again, the bottom polynomial will increase faster than the top. The denominator has x that can't be -3 and x that can't be 2. So those are going to be graphically some vertical asymptotes. So if we were looking at a graph, just a sketch, then at -3, there'd be an imaginary vertical line. At +2, there'd be an imaginary vertical line. The y equals 0, I'm going to do in a different color just so you can distinguish. Okay. And then the numerator, the x minus 1, an x value of 1 would cause 0 over a number, which is going to be 0. So x equals 1 is actually where you have an x-intercept. So you can put a dot there as an x-intercept. The other thing that you could try to come up with would be a y-intercept. And that would really be up to you to do that. And then we could also look at the graph of it, going to y equals calculator, making sure you do x minus 1 in parentheses, and then x plus 3 times x minus 2 in their own sets of parentheses. And you'll be able to see the breaks in the graph. You know, there's a portion here in this left piece. There's some cubic type stuff going on here. And then there's another portion on this right hand piece. And you can more specifically actually find this y-intercept if we plug x in for 0 for everything. If we did that, it would be 0 minus 1 on the top, 0 plus 3, 0 minus 2 on the bottom, so -1 over, let's see, that's 3, that's -2, so 1/6. That would be your y-intercept. So right here would be, you know, a crossing at 1/6, and you could get the graph a little bit more detailed. But you can pull vertical asymptotes from the denominator. You can pull horizontal asymptotes from those leading terms comparing their coefficients, depending on the nature of their relationship. You can find y-intercepts by setting x equal to 0. That's what we did over here on the right. And then you can find x-intercepts, which are your zeros. They're your solutions to the function being 0. But you have to focus on the top polynomial and where the zeros are for that, and that will give you the zeros for the function that are available. The only additional thing about horizontal asymptotes that I want to mention, that was mentioned a little bit a few minutes ago, is that horizontal asymptotes can be crossed, whereas vertical asymptotes cannot. And what that means is you may have a function. Did I make that there? You may have a function where it gives you a horizontal asymptote. Screen got really small. Not really sure why. You know, you may determine that there's a horizontal asymptote at y equals 1, and imagine your horizontal dotted line, but you may have your function, you know, come up and cross it, and then it'll have this hump, and then it'll come back down, and then it will start to approach the horizontal asymptote. And that's perfectly allowable in the sense of a function. They'll never cross a vertical asymptote, but they can, in fact, cross horizontal ones. It's just horizontal asymptotes tend to reflect the long term or the long run in behavior as to where that function's trying to go as x goes to positive or negative infinity. It's a long run behavior aspect, not a short term one. That's more defined by the zeros and the intercepts that we'll look at. But I just wanted to mention that horizontal asymptotes can be crossed. Vertical asymptotes cannot, because those are created by what makes the function undefined in the denominator. So those cannot be crossed in the sense of a graph, but the horizontal ones, it can be. So there's just a little, not much, but a little insight on long-run behavior with regards to horizontal asymptotes with rational functions.